Hi guys, how's it going? Terry Brown, Mechanical Engineering here with another engineering mechanics video. In this video, I'm going to do a lecture on moment of a force and this time look at the vector formulation of the moment of a force. So let's have a look at the PowerPoint. Okay, so as I said, we're going to look at the moment of a force and look at the vector formulation. In a previous video, I did the scalar formulation and looking at principle of moments and a couple of examples. So let's get the clicking happening. So the lecture objectives for this video: to understand and define what a moment is, or review what that is, determine the moment of a force in 3D cases, revise the cross product, which we'll need, and then use the vector cross product equation to determine the moment of a force in 3D. Okay, so you can just see over here a little example of some kind of a mechanical component. We've got a force applied at an angle to all three axes and at some distance from this collar that this thing is attached to. So we might want to know what is the moment that is generated about point A, for example, of this force that's at an angle to all three of these coordinate systems. So the easiest way to do this problem would be to use the vector moment equation. And I'm not going to do that in this video. I might do an example later. I'll do a bit of an easier example in this video. All right, so just a reminder, the moment of a force is its tendency to cause rotation of a body about an axis some distance from the line of action of the force. And to calculate the moment in 3D, we use the vector cross product, which is m equals to r cross f. Okay, so r is the position vector and f is the force vector. And because we have a cross product here, then the result of the cross product is a vector. So we should note that the moment of a force in general is a vector. In the simpler 2D problems, you may not realize that because we just say, you draw a little arc with an arrow on it. So when we look at the equation in vector form, we have the position vector here, and that can be to any point along the line of action of the force. So in 2D, we had to specifically say that it was the perpendicular distance. When we're using the vector form of the equation, the position vector can be to any point along the line of action of the force. And usually we'll have a choice about how we specify the position vector, and some ways of defining the position vector give us an easier way to solve the problem than others. Okay, so I've said all that, so that's just in your notes there. You can refer back to that. Again, just a reminder here that in talking about the moment of a force, it's a vector. So here we've got the vector shown acting along this axis here. And then we've got the little arc with an arrowhead to show the direction of the rotation. So using the right-hand rule, if your fingers point in the direction of the rotation, your thumb will point in the direction of the moment. All right, so I've already said the position vector R. The moment is a vector with magnitude and direction, and we use the right-hand rule. Okay, so I've just done that already. And if the force vector is in the XY plane, then the moment vector is in the Z direction. So of course, in general, the force can be in any plane or out of all three planes, as I showed you in that example before, and then we'll need to work out what the components of the moment vector are along X and Y directions. Now, the vector equation that we use must be R cross F, not F cross R. As we'll see in the next slide when we review the cross products. Okay, so must be R cross F, not F cross R. Okay, so the reason for that is that in the cross product, the commutative law is not valid, so you can't put them the other way across. So if they were scalars and we did A times B and B times A, then that's okay. But because they're vectors, the vectors do not follow this commutative law. You should have done a week or two at least of vector mathematics in Maths Modelling 1, if you're at UTS. If you're anywhere else, you might have done a different subject, but you would have done in maths, in your first year maths subject, vector operations. Okay, so if we look over here, C, the vector C is equal to A cross B, and we get the vector C going upwards. But if we do B cross A, we get the vector C going downwards, right? So we get a negative direction or a negative sense for the vector. So I'm not doing a complete review of cross products. I'm just kind of doing the main points as it relates to what we'll do in looking at the vector moment equation. So from your vector work that you've done previously, you should know that we have these unit vectors I, J, and K, which are the unit vectors in the coordinate systems X, Y, and Z. So I is the unit vector in the X direction, J is the unit vector in the Y direction, and K is the unit vector in the Z direction. And we have all of these operations. So for example, I cross J gives us K, J cross K gives us I, and K cross I gives us J. If we do the opposite to that, if we do I cross K, we get minus J, and so on. If we have cross product of two vectors that are in the same direction, then the cross product of those two vectors is 0. Okay, so if we have I cross I, we get 0, J cross J, we get 0, K cross K, we get 0. Do you need to remember all of these things? Well, you could, but the way I do it is to remember, well, these ones are easy to remember. Just if you've got I cross I or J cross J or K cross K, they all equal to 0. Right? Trying to remember what you get from I cross J or J cross I, is it positive K, minus K? If you remember this circle, right, and remember I, J, K, if we go around this circle anti-clockwise, so we do I cross J, we get positive K. If we do J cross K, we get positive I. If we do K cross I, we get positive J. Okay, so that's what we've got here. If we go around the other way, if we have I cross K, we get minus J. If we do K cross J, we get minus I. If we do J cross I, we get minus K. And fortunately, if we do a cross product is multiplied by a scalar, it obeys the associative law, so we can move the scalar through wherever we like. Okay, so that's a very quick and rushed revision of the cross product. Hopefully it'll make a bit more sense when we look at an example. So here's our example. We've got our post with the lug that we looked at for the scalar moment of the scalar formulation of the moment equation. So this time we're going to use the vector moment to work out the resultant moment about point A of these two forces. So what we need to do is to write the forces and their positions in vector notation and then determine the vector moment using the cross product. So let's first write out the forces and their positions in vector notation. So let's first define X and Y axes. So we have X horizontal to the right and Y vertical upwards. In order to write the force in vector form in IJK notation, we need to know what the components of the force are in those directions. So again, we'll need to do find these Fx and Fy's. We did that previously, so hopefully you know how to do that. So once we have these components in the X and Y direction, they are just scalars multiplied by the unit vectors. Okay, so we have 400 cos 30 times the unit vector in the X direction. So the unit vector I in the X direction. And then we have 400 sine 30 times the unit vector J in the Y direction. Okay, and here I've just taken the 400 out the front because it multiplies to both terms. Okay, so that's this vector, our vector force over here, and then we've got our weight force. So it's just going in the minus y direction, and it's magnitude of 100, so scalar minus 100 times unit vector j. Okay, so let's now work out the position vector for F. Easiest thing to do here is to say the position vector from A to the point of application of the force here. All right, so let's do that. Let's draw it in first. That's what we're looking for, and starts at 0, 0. So writing the position vector is easy in this case. It's just the coordinates of this point here. So 0.5 meters times the unit vector I in the x direction plus 0.9 j unit vector in the y direction. Okay, let's now do the position vector for W, and same thing. I've just, in this case, just put the position vector to this point here. Now, in our problem, we're not given where this is. Okay, so I'm going to assume that it's at point A. Now, hopefully you can foresee that in this case, it doesn't matter what we assume for the y location. Right? So we could, or as I said before, the position vector, we can define to any location along the line of action of the force. Right? So I could have done up to here. So I could have said it was 0.9 instead of 0.8, or I could have said the position vector was across to here and the y location was 0. Okay, so anyway, let's just do it as it is and see what happens. So we've got here now 0.2 I in the x direction for this location, and 0.8 we've assumed in the j or y direction. So now let's determine MA using the vector cross product. So we have the sum of the force times the vector positions, so we just need to add them up for the total moment. So we have R subscript F for the position vector for the force F times the force, and the position vector for the weight. Okay, so now let's do the cross product for the applied force over here. So we have R cross F, and R was 0.5 I plus 0.9 J times the force vector, which was 400 times cos 30 I plus sine 30 J. Now there's ways using determinants and so on to do these cross products of vectors. But what I like to do here is to just keep it simple and just show you how you can multiply through to get the answer. Okay, so it's a little bit slower and more tedious, but hopefully a little bit easier to understand. All right, so what we've got here is to multiply through each of these terms here. So we can put the 400 out the front, and then we've got 0.5 I times cos 30 I. Okay, so that's my first term here. So we get 0.5 cos 30 I cross I. And then we have 0.5 I times sine 30 J. Okay, so that's what we have in the next line here. So we end up with I cross J. Then we multiply this term through the second term again. Right? So 0.9 J times cos 30 I. So here 0.9 cos 30 J cross I. And then 0.9 J times sine 30 J. So that's what we have here. So as I showed you before, if you have I cross I and J cross J, so cross products of two vectors in the same direction, that's equal to 0, so they're going to drop out. And here we've got I cross J. So if you remember IJK, IJK, so if we go around I cross J, we get positive K. And then here we've got J cross I, so we're going the opposite way. So J cross I will give us minus K. So if we do that, we'll end up with this expression here. So we can see that here we've got 400 outside of 0.5 sine 30 I cross J becomes K, and then here 0.9 cos 30 j cross, well, over here, j cross I becomes minus k. And so we get minus 211.8 unit vector k Newton meters. So be careful how you write this. Right? Don't stick the k onto here, because then that looks like kilonewton meters, which is what I nearly said then. So now if we look at the weight vector here, the position vector that we chose was the position vector for the location that we chose up here, 0.2i plus 0.8j cross minus 100j. So if we, I haven't spelled this one out, but we know that j cross j up here is equal to 0, so that drops out. And so here you can see it wouldn't have mattered what we assumed for the position in the y direction. We could have had 0.9, we could have had 0, wouldn't have mattered. Okay, still get the same answer. So the only thing we're left with is 0.2 I cross j, and I cross j is k. So we end up with minus 20k Newton meters. As I said, you can now see why that didn't matter. And if we add all of this up, we get minus 232 in the k direction, right, or the z direction, Newton meters. Right, so this is the same answer that we got previously with the scalar method. Right, and also note that the negative sign that we ended up with here indicates that we've got a clockwise moment, right, which is what we saw before. Okay, we didn't have to make any assumption about what was positive and not what was negative, clockwise, anti-clockwise. Doing the vector method tells us that we've got negative answer here if we get all of our vector algebra correct, which is not without its difficulty. But yeah, so the negative number here tells us that we've got a clockwise rotation. All right, so that's the end of this little lecture. Hopefully that was helpful and cleared up how to make use of the cross product and use the vector equation for determining a moment. All right, bye for now. See you in the next one.